Swayam Prabha. Digital India. Educated India.
Hello everyone. So, we will continue with the module for extreme heat and fire protective clothing. So, we have discussed different types of fiber required for the this fire protective clothing. Now, let us discuss about the fabric structures and design. So, to see the role of weave structures. So, we have different types of weave structures. So, for woven fabric, a plain weave structure, it is a tight firm structure, good thermal resistance, but limited flexibility and comfort. So, the main advantage here in woven fabric is that we can produce with a very tight and firm structure. So, stability, structural stability is very high. So, we can have we can produce very compact fabric with good thermal resistance, but as far as the body fit garment is concerned, we need stretchability. So, in woven fabric the stretchability is not there like knitted fabric. So, in plain fabric another problem is that it is due to very compact the number of interlacements are very high. So, the flexibility is less. In twill weave, so as we have already discussed, diagonal pattern is created. So, it is a little bit more flexible. So, better drape and mobility and moderate penetrance protection due to less compactness. It is not that compact like plain weave. So, here we will get moderate protection. The structure is not that compact like plain weave. Now, satin here floats are longer floats and that is why surface is smooth. So, lower thermal resistance due to longer float and heat penetrates easily through the satin fabric because of there is a chance of thread distortions. Honeycomb weave is a 3D cellular structure, higher thickness and air entrapment is there. So, that it will that this due to this air entrapment, the excellent insulation and protection due to cellular structure, fire protection, it has been observed that fire protection is higher than plain weave or twill weave. Knits and nonwovens are also used for protection, fire protection sometime. Knits, the advantage here is it is a flexible, lightweight, it is used basically for inner layer for comfort in flame resistant clothing. So, inner layer we need higher movement, body movement and it needs flexibility. So, for inner layer knit fabric may be used. Nonwoven basically it is the advantage of nonwoven, it is a high bulk. Okay. So, that insulation is very high and that is why it can be used as in the inner layer, acts as thermal barrier against flame and radiant heat. So, due to higher insulation and here radiant heat, that means we can make compact nonwoven also. So, enhanced fire protection can be engineered with aramid, PBI or FR treated fiber. So, we can use this type of fibers for enhanced fire protection. So, moisture and heat management is very good through the neat fabric, which allows the sweat evaporation easily, and non-woven, the advantage here is it can trap steel air and which acts as insulator. So, in application, if we see integral in multi-layered system for firefighter suit. So, we can use non-woven in one of the layers, in foundry clothing also, and arc flash PPE. So, this type of applications non-woven is widely used. Now, knitted fabrics in heat protection. So, where we will see where the flexibility is required, body movement is vital part, frequent body movement like your gloves, where we have to grip the hot or grip the different types of objects, and at the same time we need fire protection. So, it is flexible and stretchable, improving wearer mobility. So, where the mobility is high, so in those cases knitted fabrics are used. Open structures enhance breathability, but at the same time it lowers thermal insulation. So, we have to engineer the structure in that way, can be engineered with fire retardant fibers to improve protection, often used as comfort or inner layer of multi-layer protective clothing. So, generally we use knitted fabric, as I have mentioned, for inner layer. So, the limitations are due to its loose structure, it allows heat and flame to penetrate easily. Poor dimensional stability under high thermal exposure, because it get shrink easily due to loose structure. Limited durability compared to woven fabric, because woven fabrics are much more compact and structured. Here the durability is less because of the loop structure. Loop can get distorted easily, particularly weft knitted structure requires blending with high performance fiber for effective use. And as far as non-woven is concerned, for heat protection application, it is basically used in inner layer, high thermal resistance, and it has low thermal conductivity we can create due to porous structures and open entrapped air, lightweight due to very low density, highly porous, and typical aerial density 50 to 200 gram per square meter we can use in case of fire protective clothing, and due to its open structure it ensures comfort while maintaining insulation. Superior barrier performance, LOI of flame retardant non-woven is more than 28%, although that depends on the type of fibers used. Effective against flame and molten metal splash. Okay. So, non-woven can be used for molten metal splash protective clothing. It is enhanced protection with treatments. We can treat the non-woven to enhance the protection by treat by ceramic or aerogel coating, which achieves 30 to 40% thermal resistance compared to untreated fabrics. We can increase the thermal protection performance of nonwoven fabric by treatment. The limitations are due to its low strength and abrasion resistance compared to woven fabric. So, it can get damaged due to abrasion quickly, dimensional stability under repeated stress or laundering. So, it can change this dimension, may degrade faster in long run due to thermal exposure. Because of the open structure, heat penetrates inside the structure, that flame can penetrate inside the structure, often require lamination or reinforcement for durability. We can laminate for enhance durability. So, the 3D spacer fabric also is used for thermal protective or thermal barrier. So, excellent thermal insulation due to thick open space provided within the structure, the thick 3D space. So, typically 4 to 10 millimeter space provided low thermal conductivity, okay, because due to air entrapment. So, it is the thermal conductivity is as low as 0.03 to 0.04 watt per meter Kelvin. High thermal resistance value because of the air entrapment. So, air's thermal resistance is much higher than the any fiber. Spacer fabric achieve thermal resistance of 0.35 to 0.5 square meter Kelvin by watt, significantly higher than the flat woven fabric. So, you can see it is typically 3 to 4 times higher. Improved moisture and air permeability because of the open structure. Because of the open structure 3D structure, the air can because an open structure. So, air can transmit very easily. So, and the moisture vapor transmission is very high, more than typically 1 liter per square meter in 24 hours. So, which enhance the comfort. So, we can achieve higher thermal resistance with improved air transmission and moisture vapor transmission. So, for those applications we can use the spacer fabric. So, and structural stability under compression, because the in the spacer fiber the spacer yarns are typically in vertical orientation. When the it is loaded compressed from the top. So, this vertical oriented the filaments are buckled. Okay. This is the, and when the load is applied it gets buckled, and after load removing the load, this vertically oriented filaments are they are again become straight. So, that is why it maintains the structure, structural stability is very high, retains 70 to 80% thickness of after cyclic loading, which is very good, long term durability and protect. So, its porosity is maintained, almost say 80% porosity is maintained after the repeated loading. So, that actually and that is why it keeps the thermal insulation very high after repeated loading. Now, we can enhance the functionality by coating and lamination. You can see enhanced thermal barrier. The coating may be done by polyurethane, silicone or ceramic, which can reduce the heat transmission by 25 to 40%. So, if we can coat it with thermal conductivity as low as 0.025 to 0.035 okay, watt per meter Kelvin. So, we can enhance the thermal resistance. Okay. High flame resistance. So, these coatings PU silicon or ceramic coating this can provide high flame resistance. So, laminated fabrics achieve LY value more than 30%, so which is very good, meeting NFPA 2112 standard and ISO 11612 standard for protective clothing. And it improves the mechanical durability due to coating on the non-woven fabric. Fibers do not come out after repeated say after while abrasion. So, coated fabrics show 20 to 30% higher tensile strength and tear strength compared to uncoated base fabric. Even the abrasion resistance also increases. And superior barrier properties. Laminations provide more than 90% resistance to molten metal okay, penetration. So, due to this coating, so molten metal penetration is actually that reduces drastically, maintain thermal resistance up to 300 to 350 degree exposure. So, this fabrics this coated and laminated fabrics can be used for very various applications. Now, let us try to see the 3 layer arrangements of fire protective clothing. So, this is usually 3 layer fabric structures are used to enhance thermal protective performance. So, we do not normally use the single layer. Single layer is always difficult to create, and the requirement of fire protective clothing are multidimensional. One is that it should protect from external environment, that may be say fire, flame, maybe radiant heat, maybe water splash, maybe anything like molten metal. So, there are many such external parameters are there. At the same time, the inner heat, that body heat should come out in the form of moisture vapor. So, there multi dimensional requirement cannot be met using a single layer fabric. So, typically 3 layer arrangements are there. One is outer layer, middle layer and inner layer. So, we will discuss these layers, what are these layers, what are their functions. So, and what type of fibers are being used in different layers. So, let us try to discuss here. So, we can see here the outer layer, it is a cell layer, okay, and then this is the moisture, the thermal layer which actually prevent the heat to penetrate, and moisture barrier layer which is laminates on the thermal layer, and that is basically used to prevent any outside fluid to the body from the penetration from through the fabric, and at the same time body moisture should actually get out through this moisture barrier layer. So, that is the function. Now, let us see the outer layer. So, its other name is thermal protective layer or reflective layer. Reflective layer is for basically radiative heat reflection. So, that outer layer we can use reflective layer, and or shell fabric. shell layer we can use. Okay. We can other outer layer also we can call it as shell layer. The purpose here is it should provide resistance, it is a resistance to ignition and protection from the different radiant heat and flame. So, it protect the wearer from radiant heat and flame. So, it should not be flammable. So, it should resist the fast flame or heat comes in on the outer layer. It should be protective layer and provide high breakage strength. So, breaking strength should be high, because the main load comes on the outer protective layer. So, that is why that this is the breaking strength should be high. If that outer layer fails, then the heat can easily penetrate inside, provide resistance to mechanical hazard like any tearing, abrasion. So, this layer will actually face all the mechanical hazard and protect the inner layers and also the human body. It should be cut resistant, it should be abrasion resistant, tear resistant. So, this type of mechanical hazard the protection this outer layer should have, and it should not accumulate static electricity. So, that is very important. If it accumulates, then that there will be different types of problems can occur. So, static electricity it should not be there, and provide resistance to chemical, hot water absorption and thermal shrinking. So, thermal shrinkage should not be there, then the total performance of the body where this 3 layer structure will get destroyed, and that is why, and main heat comes in the outer layer. So, it should not get shrunk, shrinkage should not be there. Now, what are the materials used? Mainly aramid fibers and their blends are used. So, blends are mainly used to reduce the shrinkage performance of aramid fiber. So, Nomex 3A is a blend of aramid fiber, where small amount of other fibers are added. So, Kevlar and Nomex blend. So, aramid, para aramid, meta aramid blend, and at different proportion one can use. PBI fiber also used, and also its blends are used 50-50 with a Nomex and PBI fiber, 75-25 Tenlon fibers are used. Coated materials, because we should have different types of coating like water or treated fibers, water repellent finishes are used, or PU coated that we have already mentioned, ceramic coated to enhance the thermal protective performance. Aluminized coated Nomex fabric fiber. So, aluminized coated what we use, because it of the high radiant heat protective clothing, we can use aluminized coating. Aluminized coated glass fiber. So, different types of aluminized coated fibers are being used. Now, the middle layer if we see, its other name is moisture barrier layer. The purpose here is the resistant to radiant heat and flame, provide breathability to the structure due to the moisture barrier. It contains micropores within the structure, where the moisture vapor can pass through. So, avoid penetration of moisture inside the fabric from the environment. So, that is important. So, if you are creating a moisture barrier layer with a pores, very small pores, the water from outside, water from outside will not be able to penetrate, but moisture vapor from human body will go outside. So, that to keep the human body dry and comfortable. So, it allows some physiological heat by evaporation of moisture to pass through and provide comfort, as I have mentioned. So, as the moisture vapor passes through, it takes away heat, latent heat from the human body. So, if we do not use the moisture barrier layer, and if it is there, and at the same time if we want to have it waterproof, then if we block the pores, then the body will be heated. Okay. Unnecessarily the body will be heated. So, it also provides resistance to chemical hazard and protects the wearer from external hot water and liquid. So, any time that hot water can come, any hot liquid splash can be there or chemical splash may be there. So, that it protects. The materials which are used, so basically aramid fibers and its blend they did fabric. So, that the fabric, base fabric may be nonwoven fabric is basically aramid and its blend, and that will be laminated with flame resistant or retardant material, and this laminates are porous laminates, that has to be that, and pore size can be controlled. So, aramid fibers and its blends, the materials like Nomex 3A, Kevlar, and they are blend like similar to the outer layer, but here the advantage is the main difference is there here, it is a coated material. Polyvinyl coating can be used, polyurethane coating, and polyester sulfone PES, okay, that coating can be used. Okay. And a regenerated cellulose fiber viscose with flame retardant, okay, coating materials, that can also be used here, because this moisture barrier layer, the temperature where temperature is not that high, in those cases regenerated cellulose can be used, and if it is very high temperature, then this fibers may get degraded depending on the application, and PTFE with PU coating materials as a coating material we can use. Now, coming to inner layer, its other name is thermal liner. Basically, it is a or thermal barrier where the main entrapment of air is there, and which acts as a insulating material or thermal barrier. The purpose here is mainly it should provide resistance to external heat flow through the clothing. So, it is bulky in nature, and that will entrap air, and it will be insulating in nature, provides high breaking strength to structure, provides resistance to the mechanical hazard and chemical hazard. So, that is its purpose. So, it should be stable and exhibits good thermal insulation property and provide comfort characteristics. That is very important. It should give the sufficient comfort characteristics. And if we see the material here, similar materials are used. The aramid fibers and their blends, which was used in case of other 2 layers Nomex 3A, Kevlar and their blends. Same fibers can be used here also, because it should be heat resistant. And here one thing is that as main function here is to give the thermal protection, thermal insulation. Here we can incorporate aerogel, maybe within the structure or maybe in the form of coating. So, aerogel aramid fiber based composite also can be used. Okay. Here we can make a composite that will be flexible, and aerogel main advantage is that it contains large quantity of air and its structural stability will be maintained. FR cotton and its blends can be used. So, let us now try to understand what are the different factors in a clothing, in a textile material, which affects the thermal protective performance, TPP rating. So, there are different factors available here. Now, TPP rating, what is this? So, the effect of thermal intensity or heat flux, okay, and the type of thermal exposure. So, that is TPP rating changes. Okay. So, like if we increase the thermal exposure, okay, that will change the TPP rating of a particular fabric, like radiative, whether it is a radiative exposure or whether it is a convective or like a flame exposure, or whether it is a combination. So, for a standard testing, standard test they actually specify what type of exposure it is there. If we follow a particular standard, that will clearly specify what is the intensity of the of thermal source, heat intensity, or what is the rate of heat flux that is there, and type of exposure. So, everything will be specified for a standard and we must follow that particular standard. So, TPP rating depends on all these parameters. So, we have to have a TPP rating for a particular fabric, we need to follow a standard procedure. Okay. And what type of air gap has to be maintained. So, air gap is also whether the sensor will touch the fabric or there will be certain air gap. So, the sensor is nothing but it actually simulates our skin. So, if there is any gap microclimate, so then in that case TPP rating will change. So, that is why the effect of air gap is also important, and depending on the air gap the TPP rating of a particular fabric changes. So, if we keep the intensity, heat flux or type of exposure constant, but for a particular fabric the TPP rating may change with the change in air gap. If we reduce the air gap, the TPP rating will be lower. That is how we must specify the air gap. And the fabric related parameters are the fabric thickness is there. If we change the fabric thickness, the TPP rating will change. Fabric bulk density, if we increase the fabric thickness, TPP rating will increase, like that. So, moisture content in the fabric, if we change the moisture content, then TPP rating will be different. So, keeping air gap and other parameters same. So, the TPP rating will change with all these parameters. Fabric weave structure. So, for a compact fabric, the TPP rating will be high, okay, or fabric with higher aerial density. With higher aerial density, then TPP rating will be high. So, that all these parameters affect TPP rating. So, there are basically you can divide it to 3 type. One is the flame or exposure, fire exposure or heat exposure related parameters, intensity, heat flux and type of exposure. So, whether it is a radiant, flame or combination. And second parameter which affect the TPP rating is the air gap, presence of air gap. So, if we increase the air gap, the rating will be different. And third one is the fabric related parameters. Now, the parameters, let us see how are this affecting, all these parameters affect the TPP rating. Now, we can see fabric thickness. Okay. If the fabric becomes thicker, so it will increase the TPP rating. Why? Because it will actually store either more air pockets or fabric thickness, maybe if we keep the aerial density and increasing the thickness means there will be more and more air pockets. So, that will increase the conductive heat transmission, or fabric thickness increases with the increase in number of fibers, that means aerial density at the same time it increases. So, it is important for radiative and combined type exposure. Okay. So, low intensity flame exposure. So, this type of situation we can increase the fabric thickness. So, with a low intensity exposure, so that in that case the air pockets, keeping the aerial density constant, if we make the fabric more porous, the TPP will increase, okay, mainly for low intensity flame exposure or radiative and combined exposure. So, aerial density, if we increase the aerial density, then the TPP will be rating will be more, because high density woven fabric is used, because the aerial density is higher, high density woven fabric is used as outer layer and a bulky knitted fabric as a inner layer offer better thermal insulation. So, if we increase the because here number of fibers in the cross section of the fabric will increase. So, that will prevent the radiative heat penetration and at the same time convective heat penetration. So, flame and radiative heat, in both the cases it will improve the TPP. And thermophysiological properties, you can see thermophysiological properties increases, that means thermal conductivity and surface reflectivity plays important role. So, important role in thermal protective for low intensity and long duration. So, for those, so surface reflectivity is very important, and heat capacity of fabric plays also an important role in case of short duration. Now, next parameters are intensity of flame exposure. So, if we increase the intensity, then the TPP rating will decrease. That is important for keeping the fabric constant. So, TPP rating will, so heat gain from far infrared radiation increase for high intensity radiation. Okay. So, higher intensity radiation and decreases as wind speed increases. So, in case of high wind speed, so that TPP rating will decrease. Thermal energy storage, if it increases, it is vital in case of thicker fabric, okay, and in presence of moisture. So, thermal energy storage is that aerogel, okay, aerogel if it is increases, increase the TPP. So, aerogel treated thermal barrier layer, it becomes lightweight and excellent insulator. Air gap width. So, if we increase the air gap width, TPP rating will increase. So, that we have already discussed. And shrinkage, shrinkage is basically it initially increases then decreases. So, fabric the fabric's thickness increases, thereafter due to the pyrolysis it decreases. Okay. So, performance retention analysis after repeated flash exposure. So, this may also happen if we treat the fabric up by repeated exposure. In that case the performance the same performance may not be retained. Now, let us see what is that. So, surface area retention. So, when we repeatedly expose the flash fire, okay, the fibers, the fabric may get shrink. Okay. The due to the shrinkage, the surface of the fabric, in the surface of the fabric, okay, shrinkage if it is there, the cloth will tighten. Thus, it will impact the mobility of the body part. So, outer surface will get shrink and it will become tightened and the body mobility will get affected. Thickness retention, so higher the thickness better is the protection. So, that is we have discussed. Mass retention. So, higher repeated heat exposure, mass continues to decrease, okay, and due to that protection level of the clothing reduces. And TPP retention, thermal protective performance, and to analyze how the second degree burn time changes with the increase in number of exposure. So, that can be tested after repeated thermal exposure. So, that typically it drops due to all other factors which has been discussed. Now, we will discuss the how to measure the thermal protective performance, and we will try to see a few methods which are developed in house, and we will discuss here. Now, this is thermal protective performance for the radiant heat. So, radiant thermal protective performance tester, where TPP rating is calculated, calorie per square centimeter is calculated, burn time and incident heat flux. Okay. So, second degree burn time we have in second, and if we multiply it by incidence heat flux calorie per square centimeter second, then we will get the TPP rating in this instrument. And here the heat source is there, and the sensor is copper calorimeter, and we get the TPP. Now, you can see that this is the copper calorimeter which is movable. We can change the distance from the fabric, air gap distance we can maintain, and the heat source is the radiant heat source, okay. And then the calorimeter is copper sensor is connected with the computer to get the data, and here we can use the different types of fabrics, woven, non-woven, different types of fabrics we can use. Now, try to see the video. So, the computer monitor is set here, we are feeding the data, what is the requirement, what is the heat source, what is the intensity of heat we are maintaining, what is the gap, all this input data is being fed. Now, we will start the instrument and the data will be stored in a file. You can see here, now it is fabric is being placed and copper calorimeter here, air gap we are not maintaining the keeping the air gap, we can change the air gap here. Now, the heat source is heat intensity is adjusted here. Now, intensity is adjusted and now here the data we are collecting the and calculating the TPP rating here, second degree burn time, that is being calculated through the software. Now, here this is the instrument which has been discussed earlier. And other machines we have developed here. So, two types of instruments we have developed, one is in the vertical fabric is kept in a vertical side, this is the vertical orientation, another this is the vertical orientation here and we can have also the horizontal orientation. Now, let us try to see the TPP tester. Okay. Okay, now see that this is the setup where fabric is being placed in horizontal fashion and the flame is actually projected from the bottom. Okay. Now, you can see the video of this. Now, you can see the flame intensity is getting adjusted to have intensity of the. Now, this is the flame has started here and we can see that after certain time the flame is actually exposed here and we can make it automated also, and after certain time of say that we close it after testing. So, that is closed now and the data is being captured in the this by the calorimeter and we can get this tested and we can analyze this thing, and also after that we have taken the fabric out of that, what are the changes in the fabrics, that also we can analyze. Now, another instrument is the this where the fabric is kept in the vertical motion, vertical direction, and here the advantage is that in this equipment the two flame burners are there, which is we can change the angle, typically is 45-degree angle orientation, and along with that the you can see the radiant heat source is also there. In this instrument we can have both flame and resistant radiant heat and their combination. So, all these combinations we can have only one single only flame or only radiant or both. So, we can see here this instrument. Now, see this is the instrument here, we can see the total video running. Now, here this is the chamber where we can change the moisture vapor, which actually shows our microclimate. This is microclimate. Okay. Now, I can little bit. Now, here you can see these are the two burners, maker burners are used here. Now, the fabric is placed inside the chamber. Okay. Now, this is there is a fabric grip is there, you can see this is the fabric grip. Okay, fabric grip is there, and the moisture, if we want the moisture vapor, so that can be also we can pump moisture vapor to control the humidity. At different humidity level we can use this instrument that we can measure the TPP rating. You can see here just here is the pins where we can place the fabric, and this is the copper calorimeter, which actually resembles our simulate our skin, what type of temperature it will be, it will come through the fabric, and it is connected with the computer. This is connected with the monitor. Okay. Now, you can see, now we can change the distance of our copper calorimeter from the fabric. Fabric is being placed, we can see that how the fabric is placed, that if we try to see placing of the fabric, this is okay. Just we have cut the fabric and just simply we have pushed the fabric through the pins. Now, the instrument will start the instrument. Now, here see, these are the two burners, okay, and this is the radiant heat source. Now, this is manually we can ignition is manual ignition. Now, this is the fabric is placed here, and after this placing of fabric we will close it, and this is the barrier. Okay, that barrier plate we remove the barrier plate once we start the testing. Okay, testing. So, after flame has been started, the burner is started, then the barrier is removed immediately after that. Now, you can see here, now the instrument is now ready for testing. So, this is closed and we have adjusted the air gap, we have set the instrument. Now, you can see here now the intensity of flame or intensity of the radiant heat is adjusted, like earlier only that is for only for radiant heat, here it is adjusted. So, we can adjust the this flame exposure also by the knob from the gas cylinder. Now, the radiant heat has started. Now, it is we are now changing the radiant heat exposure. see that, see this is the radiant heat. Now, test has started. Okay. And after this test, this samples will be, the data will be recorded accordingly. This is for radiant heat. Now, we can do on the flame also. Just see flame intensity has been adjusted, and by manual ignition. Now, flame is it is as per required. So, flame exposure is there. So, we have recorded the data, and here flame and radiant has done sequentially. We can do simultaneously by adjusting the, now here you can see the both flame and radiant. So, depending on our requirement, we can test our specimen accordingly, and then the all this data will be analyzed. Here you can see the different components of the instruments. Here it has got different components here. Now, you can see the maker burner. This maker burner is responsible for the flame and flame intensity, and we can see here in between, this is the system here. Here temperature sensor and humidity sensors are kept here, and this is the fabric specimen as I have shown. This is the fabric specimen here, and this, and here is the copper calorimeter. Now, this is, and through this pipe the moisture we can pump in to control the to change the relative humidity, and this distance can be adjusted, as I have shown. This distance can be adjusted to adjust the microclimate thickness, and here we can see this is copper calorimeter, this is the pins and fabric, and copper calorimeter is connected with the computer. So, maker burner is kept at certain angle, typically it is a 45-degree angle, and then the quartz lamp is for the radiant heat, and here we can see the fabric specimen is placed here. This is a fabric specimen, and you can see the air gap is there, and on the other side the sensor assembly, that is copper calorimeter, and it is connected with the computer, and this is microclimate, this air gap, that is microclimate, and where the temperature and water vapor it penetrates to control the relative humidity, and relative humidity is measured with the help of the humidity sensor, and temperature is measured with the temperature sensor. At real time it is measured, and the air gap can be changed by moving this slider with the help of slider, and the shutter is there, and when the at the time of test, at the start of the test, the shutter is removed. So, the heat is exposed to the fabric is exposed to the flame or radiant heat. This is the flame and the radiant heat, it comes, now shutter is removed, and then test start. This is goes, and what that convective and radiant heat comes to the fabric surface, and then heat is being transmitted, and the calorimeter is receiving the heat, and which is calculated, which calculates the second degree burn. Okay, this is the convection takes place, and then through the computer we calculate the second degree burn, and here we get the, with the help of Stokes curve we get the tolerance time, tolerance time, and accordingly we calculate the second degree burn time and TPP rating. And second degree burn time here as where the this curve sensor's response is actually intersect with the Stokes curve, and that is termed as the second degree burn time. Here as far as this figure is concerned, it is 8.1 second. So, this is the 8.1 second time. So, we will stop here and we will continue with this topic in the next session. Till then, thank you.